Welcome everyone to Defender for Cloud in the Field. Once again, thank you very much for your audience. If you are not a subscriber for the Microsoft Security channel, make sure to hit the link below and subscribe to this channel. Hit the bell to get notifications when new videos are come up. In today's episode, we have some really interesting topics to talk about. Very unique. Last time that we record about this was probably 1.5 years ago. It's about Defender for Storage. And for the first time in the show, we have Eitan Shteinberg with us. Eitan, thank you very much for being on.
Thanks for inviting me. Great to be here.
Absolutely, my friend. It's great to have you. And this is going to be a very interesting episode. It's a hot topic. A lot of people talking about storage and all the things that are going on. So let's get started with a really interesting question, which is a broad question, not really about Defender for Storage, but more about the attacks and the threats. So what are some of the known threats to cloud storage workloads?
Okay, so I have a slide on that. I'll cover briefly the threat landscape and the attack surface of cloud storage services, and I'll start with a few numbers. Looking at the most common data breaches taken from last year's Verizon Data Breach Investigation Report, we can see that 64% of attacks are originated by external actors using social engineering, compromised identities such as using phishing campaigns, and there are a lot of cases with anonymous access to misconfigured resources in the cloud. Approximately 36% of all attacks are originated from internal actors, and this number is assumed to be higher because it's harder to catch. And by the way, 10% of all attacks in 2021 were ransomware attacks, and this domain comes with a whole bunch of worrying statistics. Microsoft Defender for Storage offers unique detections that cover these threats to detect unusual behavior, malicious activities, credential abuse, and much more. And our team is focusing on the following areas because we recognize these are the top concerns that customers have, and these are the most prevalent attacks today. So uploading malware because storage is an entry and a distribution point into the organization, exfiltration of sensitive data. Storage services are used to store sensitive business and customer information, and cloud ransomware attacks. If malicious actors gain access to storage accounts, they can delete, modify, and encrypt data within the storage accounts. In some cases, these attacks occur after they've already exfiltrated the data. The values that lead our product and roadmap are to cover the top threats in all steps of the attack chain. And if we will look at the possible impacts on the storage workloads, there are quite a few. Most people distinguish between the possible impacts by looking at the required access levels to the storage containers or file shares. Storage resources that allow public access, and private resources that block unauthenticated access and only allow access with credentials, keys, or access tokens. The impacts on the resources that block public access are usually more significant because in their nature, these resources may store sensitive data. If threat actors try to attack resources that allow public access with the right tools, methods, and security breaches, they may exfiltrate sensitive data when the access level of the resource is misconfigured, in some cases even find authentication data to access private resources. It is not uncommon that this type of information is accidentally left in the code or configuration files and then uploaded to public locations. If threat actors manage to access private resources, they may upload malware to infect the account and distribute malware across virtual machines. This is especially the case if the storage account is connected to VMs with file shares, corrupt data by deleting or encrypting it, deny access to the account and damage the business processes, change permissions for persistent and future impacts, host phishing campaigns because Azure is a trusted provider and threat actors are exploiting it. And threat actors can also move laterally to other resources. And we look at how these impacts are achieved. If we'll do it, or more accurately, what are the potential threats that lead to them, we can see that looking at the authentication type is very important and not necessarily focusing on the access level to the resource. Attackers can search for existing storage accounts, and after finding them, they scan and list containers to expose the ones that allow public access. This can also be achieved by finding data with search engines like Google Dorking or Shodan. And once containers and blobs are exposed, attackers can gain unauthenticated access to the account and exfiltrate the data from there. In other cases, if attackers find containers that are open to public access, they may then find authentication data and then pivot to private containers. If attackers have managed to steal credentials or access tokens, move laterally from compromised resources, or find authentication data that was accidentally published or leaked online, they can gain unauthenticated access to private resources. And some access levels, such as gaining storage access keys, enable full control of the storage account if the access with keys is enabled on the storage account. Another big threat is the malicious insider, who can use credentials or tokens to gain authenticated access to private resources. And it's harder to spot that because it looks like normal activity in the account. So we can see there are numerous threats on storage workloads in the cloud. And this is exactly where Defender for Storage comes in. We help with recommendations to strengthen the security posture, networking, and access to the storage account. We help minimize attack surfaces and preventing attacks from happening. But we realize that there's always room for human errors, especially in face-based companies. And you must have activity monitoring and active detections in place because breaches do happen and they happen quite often.
Okay, that's a great overview, Eitan. So based on that threat landscape, what are the detections that we have for Defender for Storage?
So Defender for Storage provides numerous detections that reside in different layers to fully cover the attack chain, from scanning and exposing resources, examining access patterns and usage patterns, to identifying possible impacts on the workloads. The detections provide context and explain what happened so we can respond on time, understand the chain of events, and harden the security posture. We constantly work on improving the detection logic, cover more scenarios, and act upon feedback on security alerts coming from different sources to really improve the quality of detections and reduce the noise.
Interesting.
And the service offers a pretty rich detection suite that covers blob storage, file shares, and Azure Data Lake Storage Gen 2, IDLS Gen 2. We also support hierarchical namespaces. We look at who accessed the account and what they do or did there. There are different detection families, and a useful way of looking at them is by splitting them into two categories. The first one is the stateless detections. These are detections that don't require behavior baseline. Detections such as identifying malware that has been uploaded to the account, distribution of malware across virtual machines, dangerous misconfigurations of container access levels, hosting phishing campaigns on accounts, access from suspicious applications, suspicious IP addresses, Tor exit nodes, and we even cover successful and failed attempts to scan publicly open storage containers for sensitive information. The second category is the stateful detections, where we build baseline models that depict behaviors within specific scopes that are defined for each detection. This means that we look at unusual and suspicious activities that with tailor-made algorithms at different levels at the subscription, storage account, and container or file share level. Using stateful detections, which are in some cases are based on machine learning algorithms, we can identify anomalies in reference to the usual behavior and alert on them while providing context, such as why they were triggered. We look at suspicious access patterns, such as suspicious anonymous access to the storage account and suspicious authenticated access that came from unusual locations or unusual applications. We also look at suspicious behavior that may result in impact on the account, such as suspicious data exfiltration, data deletion, and unusual file uploads. We also look at unusual activities of access inspection, data exploration, and suspicious changes of resources, permissions, access levels. So this is a very comprehensive detection suite that we're proud of, and we're constantly improving it.
Yeah, it's
And
what now? Just to interrupt you real quick, you show all the potential detections, and one of the questions that usually comes up is how these suits work. Do we need to just enable the plan and everything is done on the back end? There is any performance issue when you enable the plan? What type of things are done for you to be able to analyze this data and then provide those insights?
okay, so it's a great question. Before I answer it, I just wanted to cover a specific question that we get a lot from customers, and it's what if the account, it's a specific use case that is pretty common, and it's what value do I get if the account blocks public access, is inside the virtual network, is only accessed through a private endpoint? And in this case, we actually have three major invalid threats that we discussed about: the malicious insiders, compromised identities, and lateral movement within the private network. And we can really see that some detections are, in fact, not relevant in this case, and some are semi-relevant and are providing a lower security value when triggered. But the main threats remain covered, with detections that look at suspicious behavior and activities, unusual access signatures, malware that has been uploaded and distributed. So that way we cover all the scenarios and we provide value even in these specific cases. And to go back to the question about how the service works, we are looking at the storage telemetry logs. We are analyzing them and crossing the information with different data models. We enrich the data with threat intelligence information that is constantly being updated, information such as malicious IP addresses and providers, malicious applications, phishing campaigns, hash values of malicious files, and we even have honeypots deployed on the cloud to generate more threat intelligence data. And there are a few important notes here. First of all, you can always export the security alerts to any SIEM solution, whether it's Microsoft Sentinel or third-party solutions. We can't, we don't, and we won't access the data within the storage accounts. There's absolutely zero impact on performance or ingestion to the account. There's no requirement to turn on resource logs for the service to work. You can do that only if you wish to investigate the alerts further. And the service is fully regional. It means that the data never leaves the region of the storage account.
Awesome. That's a really great point about the data residency. So thanks for clarifying that. During your explanation about the different threat detections, you talk a little bit about the scanning, the process of scanning for threats. Can you elaborate more on that?
Yeah, I actually got a slide about it. And some people are familiar with the term bucket scanning or leaky buckets in relation to S3 buckets, but the concept is basically the same. And to understand the scanning threat of scanning storage containers and blobs, we first need to understand the permissions of storage containers. So I'll briefly explain it in a very high level. Let's take, for example, a storage account named MediaProd1. This account has several containers with blobs within each container. And this is important for our topic. Every blob stored in the storage account has an address that includes a combination of the account name, the service name, which is blob, the container name, and the blob name. This information forms the endpoint URL that allows access to the blob. You can configure whether to allow public access at the storage account level, which is by default set to enabled, and at the container level, which has three public access levels to it. The first level is called container, which means it is open to public access. In this access level, blob and container data can be read without authentication. It is also possible to enumerate or list all the blobs within the container without authentication, meaning anonymously, if the storage account and container names are known. The second access level is called blob, which means it is semi-open to public access. In this access level, the container information and enumeration of blobs is not possible without authentication, but blob data can be read without authentication. And if you have the blob URL, meaning the attackers can guess the full URL, account name, container name, and blob names, they can access the data. And the access level is still considered open to public access, but is more restricted than the container access level. The third level is called private, and this is the default access level when you create a new container. This access level requires authentication to access blobs, container data, and to enumerate blobs within containers. This is the most secure container access level. And it's important to note that if public access is not enabled at the account level, it blocks it completely, regardless the container access level. It means that the container can be set to container level, which is the most permissive access level, but if it is disabled at the account level, you can't access it publicly. So if we will look at the blob URL below, we can see the image pic3, which resides within a public container in a storage account that allows public access. We can see that if we know the name of the storage account, name of the container, and the name of the blob, we can simply access it if the configuration allows it, and we can check it. So I'm clicking on it, just a moment, and we can see here that the blob opens. You can see the URL, and you can see Yuri here warning us not to mess with the storage account.
Nice surprise.
So there are several ways to expose blobs with different starting points. The first starting point is scanning and guessing the names of storage accounts and discovering them. The second starting point starts after we already know the names of storage accounts. For example, we found them online using Google search, and now we can start guessing the names of the containers. And the third starting point is basically brute forcing the way into the blobs by guessing the entire URL, the account, container, and blob names. This is usually the case when the container access level is set to blob and attackers can't discover and enumerate containers, but they can access the blobs if they have the full URL. When this is the case, it usually means that the threat actor has targeted the resources and has some form of information about it. Now, if we discovered the storage account, we can now start scanning for containers. If containers are found, we can, when the access level is set to container, we can simply enumerate all the blobs within the container and exfiltrate the data. Again, if the access level is set to container and the account level allows it. And the last starting point is interesting because if blobs were exposed during the brute force scanning attempts, now the threat actors know that the account name they guessed exists and is correct. And now it is possible to discover and expose other containers and blobs, specifically blobs within the container that was discovered. It means that from this specific step, you can always go here or go backwards and start the process from scratch. Now, because, and by the way, there are other attack vectors, and these are just the main ones in this attack. Now, because storage scanning is easy to achieve and does not require authentication from the scanner, it can originate from any local machine or virtual machine. And in some cases, scanning originates from cloud resources. It can be an ad hoc activity or a continuous effort to scan the web for misconfigured cloud storage resources. And it is not uncommon to find scanning activities originating from infected and controlled bots, part of botnets. It is also common for scanners to mask their identity by using Tor exit nodes, which helps hide the scanning source and make it more difficult to investigate and connect it to other activities that will occur after the scanning activity if it was successful. And I just wanted to show a few examples.
Sure, go ahead.
Of how easy it is to discover storage accounts. So threat actors can do it manually using PowerShell or command line interface with the different commandlets or commands. But it is also pretty easy to automate this process and use scripts to do that. These scripts use dictionaries that are basically word lists of possible account names, and they simply automate the guessing process. And once the storage account name is known, we can start looking for containers open to public access. as with the storage account names, to map and expose containers, attackers guess the container names manually or use word lists of known names that usually imply containers that hold sensitive data. And this is the part where the container access level will determine if a container can be discovered and if it allows listing of blobs anonymously.
Awesome.
And this is actually, if I can, we have a few detections around this space that I can elaborate.
Yeah, let's talk. Let's go through that because my next question would be exactly around the user experience, right? So after Defender for Storage detects an attack like this, how the user experience is as far as the secure alert that we receive? What type of information is contained in the secure alert?
Okay, so to answer that, first I'll try to explain about the different alerts that are relevant for this specific case, and then I'll show you some kind of a scenario, an attack scenario, and show you how it looks in the portal. Okay, so we have several detections that cover this scenario, and the following ones are a subset of the full detection suite and can be triggered in different stages of the scanning attack. They will let you know if dangerous misconfiguration occurred, scans were performed on the accounts, if someone accessed the containers, and if someone exfiltrated data from them. So we detect successful and failed scanning attempts to discover resources, and these are new detections that we released a few months ago. There are three flavors for this detection. The first one detects successful discovery of publicly open storage containers. The second detects a series of failed attempts to scan for publicly open storage containers. And we also released a few weeks ago a new flavor that is triggered on successful scanning of containers with names indicating that they might contain sensitive data inside, container names that statistically have private access level and contain sensitive information. And very soon we'll release a new detection for scenarios where containers access level is set to blob, and the threat actors are actually trying to expose blobs with brute force approach of guessing the container blob names. And once blobs are exposed, the container is also exposed, and an attacker can target the container with more scanning variations or look at other containers within the same account like we just witnessed. We will have two variations to this detection, successful and failed attempts, and that way we will have maximal coverage of all the scanning scenarios, which are pretty common. We also detect suspicious unauthenticated access to containers by detecting suspicious anonymous read access activities to accounts that are usually authenticated. We also detect unusual and suspicious applications that access the account in comparison to recent activity. And in the scope of scanning, these detections might indicate that a threat actor has accessed the account after successfully exposing blobs. We also detect suspicious data exfiltration. And there are two variations for this: detection of unusually large amounts of data that have been extracted from the account compared to recent activity, and the detection of unusually large number of blobs that have been extracted, again, compared to recent activities. And this might be triggered after a scanning alert and indicate that data has been exfiltrated. We also detect dangerous misconfiguration of container access levels in case a container with a name that is usually attributed to private containers that hold sensitive information had an access policy change, and it was changed from private to public to allow unauthenticated access. This alert will be triggered and inform you on the possible misconfiguration so that the workload owner will be able to prevent scanning from happening. So these alerts contain information on the threat actor, the affected resource, what happened, and in a way how the attacker operated. So I'll present the scanning attack scenario quickly. This is only one scenario from a wide range of scenarios that we cover. It starts with someone misconfiguring the storage access level of two blob containers that contain sensitive business information inside, whether accidentally or intentionally. Then threat actors who continuously scan the web for resources discover the account, find the two containers that were exposed, which are now publicly open, and expose the blobs inside. I simulated this attack using similar approach to the one that I demonstrated in previous slides, with some kind of a script, but more sophisticated one. And then the threat actor is accessing the blobs and exfiltrating the data. So let me show you how it looks in the portal. So this is the storage account. We can see here that we have different containers within, and we have the two containers that we discussed about API and staging that are set to container. The rest are private. We can go to the configuration of the storage account. Just a moment. And we can see here that it enables public access. And if I go to the security attach blade, you can see that the account is active and we have a number of alerts here. So these alerts were triggered in a time window of 13.5 hours. We can see two alerts that indicate the configuration change or the access level change, that it was a dangerous change and we did it. Then we have an alert that tells us that a successful scanning has occurred and containers were exposed. Then someone has accessed the account with an unusual unauthenticated access, and then the data has been exfiltrated. So if I'll jump into the alerts quickly, we can see here that we have a lot of context within the alert description of this was a successful scanning, two containers were exposed. We can see where it came from, the user agent. There were 75 failed attempts, and these are some of the attempts to guess the container names. From there, the attacker has successfully discovered two containers. And we have here more information about the containers, the IP address, and we can see here the different operation types that the attacker used. And here specifically, nothing was extracted. We can always go to the take action and investigate further, and we have here mitigation steps and relevant recommendations and other useful information as well. The second alert tells us about the unauthenticated access, and you can see here that we have different operation types that occurred only on one container. And here as well, nothing was extracted yet. Okay, you can see here the information. And in the last alert, we can see here that data has been exfiltrated. So 18 blobs were extracted or exfiltrated from the container, a total of almost 4 gigabyte. And we have here a lot of information about this event, and we can then investigate it further. And by the way, something important that I didn't mention, to the suspicious, to the scanning alerts, we are actually adding information about the IP address. So if we know that it is flagged as malicious or it came from a Tor exit node, we're going to add it to the alert title and the description.
All right, that's great. And then it looks like there is a bunch of metadata also there available, which clearly will help customers to not only understand the insights of the alert, what happened, but facilitate the investigation as well. So because at that point on, then we will need to do some sort of investigation to understand. And this is important also in some of the alerts that you mentioned. For example, unusual amount of data that was extracted. This, as you said, this is based on previous activities related to data extraction. But I've seen some cases where it was a false positive because customer was really actually doing intentionally transfer of a lot of data. So it's very important to look at those alerts and investigate further to see if it was really a malicious activity or not.
Yeah, absolutely correct.
Yeah. If I want to enable Defender for Storage across the entire organization, what should be the best approach to accomplish that?
Okay, it's a common question that we get asked a lot. I have a slide about it. So our recommendation and best practice is to follow the next steps. First of all, start with a trial period of 30 days and see the value that you get from the service. You can enable it in different ways from the portal, PowerShell. You can use policies to enforce enablement. And one of the popular ways is to use infrastructure as code with the declarative approach, using ARM templates to enable the service. And when Defender for Storage is activated at the subscription level, when a new account is created, the service is automatically enabled on it. And this is all documented in the product page. Then monitor the usage. We know that transactions can be volatile in specific use cases, and they need to be monitored. And after a few days, you can start estimating the cost. And we have dedicated workbooks and APIs for that. Then set guardrails in place, determine security budgets, and set actual and forecasted cost alerts that will inform you if cost spikes occur so that you'll be able to respond on time. These are great capabilities that Azure provides. Then monitor the usage and underlying cost with the dedicated cost analysis tools in the portal. You can use the price estimation workbook here as well. You can also use REST API requests to ingest the data from PowerShell or CLI and even build automations on top of that. Monitoring the cost is the safest way to avoid unpredictable costs. And if it is necessary, although it is not recommended, you can always exclude resources from protection or activate protection only on specific accounts within subscriptions with the allow list approach. And this is also documented in the products page. But if you plan to implement this last step, we really recommend following a security-oriented decisions-making process with your security professionals of looking at the importance of the resource, its vulnerabilities, and the ROI of Defender for Storage in front of the security threats that the environment is facing. And this approach enables you to manage the cost of the service and maximize the ROI from Defender for Storage.
A great point, Eitan. Mainly on the last slide, on the last capability about exclusion, is we definitely do not recommend getting blind about potential attacks. But if you have to, make sure that you do a deep analysis on the threat vector, on the likelihood that that resource will be attacked, and the type of data that you have on that storage account. And also make sure that sometimes it's not only about the data itself, although the data is the most important thing, sometimes it's the entry point, because one other things that could happen is the threat actor gain access to a storage account and from there move laterally to another resource, right? So it's not only about data extraction, it's using that resources to get inside the network or inside the infrastructure and then perform different activities.
Yeah, in almost all cases, we find vulnerabilities even if we don't think there are.
Right. So make sure to perform this risk assessment of your storage account before going to the direction of disabling protection on those storage accounts. All right, Eitan, this was really a great episode, a lot of insights. Thank you very much for taking the time to share this. Do you have any final considerations about what is coming up before we wrap up?
Yeah, just a few words about our future plans for the product. First of all, we're going to continue improving the detections around the major threats of malware upload and distribution, data exfiltration, and we're actually in the process of exploring extending further the detection coverage that we currently have around ransomware attacks and provide new capabilities. And I can't say more on that specific subject. And in the following months, we are going to improve coverage and boost the performance of our existing machine learning-based detections and take them to the next level so that we'll have better true positive rate, or in the way that we put it, a better signal-to-noise ratio. These new multivariate algorithms will look at even more features than we do today on the storage account and on the actor, and will detect suspicious behavior at different resource levels. And we will also be able to explain them better. And this leads to the next item, that we're planning to add more details and context to the alerts themselves. So it will be easier to understand why they were triggered, if it is a stateful detection that looks at the, will be able to provide information on the usual behavior that occurs on the storage account, explain why we found the activity unusual, why it is considered a suspicious anomaly. And that way you'll be able to have a better understanding of all that happened and why it is suspicious. Awesome. And two last things. We're working really hard on having a faster time to detect. We have already substantially shortened the time it takes to receive security alerts in the past few weeks. We're going to take it even further and make it faster. And the last thing is, at least that I can discuss about in this session, is that our team is evaluating and exploring the protection of storage workloads across other public cloud storage services.
Eitan, this was an outstanding episode. I knew that you were baking something really good. That's why you were taking the time. But finally, we have you in the show. Thank you very much for your participation, and keep up the great work. I mean, great things coming up, I know.
Yeah, and we can even discuss them in our next meeting.
Yes, we definitely need a follow-up session on this because once new things are coming up, we will have more to share. So thank you very much, Eitan.
Yeah,
Thank you everyone for joining to another Defender for Cloud in the Field episode. Again, make sure to subscribe to our channel, hit the bell, get notifications when new episodes coming up. Thank you very much, and see you again next time.